Okay, it says find the velocity and position functions corresponding to the acceleration function a of t equals j with initial conditions v of 0 equals I plus k and r of 0 equals j minus k. So this is like a light version of the problem I did the other day by deriving the projectile formula. So you'd be more likely to get one like this on the test than the full version of the projectile formula where we had to make use of a lot of different things like the angle and the acceleration due to gravity and all that. All you have to do is take a couple of antiderivatives here and use initial conditions to find c. So a little simpler, but same sort of idea. So if you know that a of t is just equal to j, then what is v of t going to equal? The integral of that, right? So the integral of j, or 1j if you prefer, dt. So what do you get if you integrate that? Yeah, okay, so you integrate that, you get, let me work across to save some room. You get t times j, and then what do you have to add in? Plus a vector, constant vector c. And then whenever we can, we like to figure out the value of c. Sometimes we can't. But let's figure out the components of c. How are we going to do that? What do we know about v of 0? Well, first of all, if you plug 0 in this guy, all you're left with is c, right? Does everybody buy that? So from what we just developed, we know that v of 0 is equal to c. But then from the initial condition, what do you know? C is equal to I plus k. And then I would just fill this in here and do the component-wise addition. So if I do that, I get v of t with no constant. In fact, I'll write out what I get. I get t times j plus o. It's just I and k, so there is no j component to combine with it here. So I'll just write it in the usual order, I plus tj plus k. And so I've recovered the velocity functions. I'm not done, but does that make sense? Okay, now I want the position function r of t. So what do I know about r of t? And keep integrating, yeah. So integrate I plus t j plus k dt. The neat thing about the ijk notation is now when you integrate term by term just like you would if it were like a polynomial function or something like that from Calc 1 or 2. Anyway, you integrate term by term, what do you get? Ti plus, okay, so yeah, okay, so t squared over 2j, or 1/2 t squared j, plus tk, plus, I'll just call it, well, if you want to call this one C1, not that I really care, we could call them both C, it doesn't matter. Then you can call this one C, vector C2 if you like, if you want to be precise. Does everybody agree with that? Yeah? And that's R of t. Now, what would we get if we plugged in to this guy that we just found? What would we get if we plugged in R of 0? We'd get C2, and then we know from our initial condition up here, we could set that equal to j minus k. So we get R of t is equal to this stuff, except I'm going to fill in the C2. So ti plus t squared over 2j plus tk plus j minus k. Did I copy all that down right? And then, so do I leave it like that? No, you're gonna add corresponding components. So what do you get if you add corresponding components? So really, you have to focus on the this guy right here, right? So ti doesn't change, does it? What's the j component become? t squared over 2 plus that 1 right there, and then put the j right by it. And then plus, what does the k become? T minus that 1 right there. It kind of looks like you're factoring out k, and you can think of it like that, but that's really what you're doing is you're adding corresponding components, right? Yeah. And so that's r of t. And so we've got, I guess the question was to get both of them, so I will circle both of them, and then we're done.